Hello everyone, I'm Zhang from Samsung Research and Development Institute, China, Xi'an. I'm very pleased to join this workshop. The topic of my paper is automatic file management based on file characteristics. My presentation will include these 5 parts. First, some background and our motivation of this research. Second, our analysis of common files in various workloads. Third, I will introduce our scheme, file stream, and then the experimental results will be shown. Finally, the conclusion and our future work. There are some issues in performance, cost, and reliability of SSD, such as reduced performance and short lifespan. GC has a major impact on both performance and cost. As we all know, GC copies validated from the victim block to another block. It consumes bandwidth and may affect user I/O. The copied data also leads to write amplification. This shows the lifespan of NAND flash. If we place data according to data lifetimes, data within the same block can be invalid at nearly the same time, and the copied data will be reduced. This is our overall idea. Analyze various workloads, recognize data patterns, analyze and estimate data lifetimes, and finally group data. Dynamic data placement policies are generated to improve performance and lifespan and reduce our latency. In this paper, part of this work has been done by machine learning, and we hope that AI can do most of the work in the future. In addition, this paper is based on multi-stream technology. Data carrying different stream IDs are placed in different blocks of SSD. There are lots of data, lots of I/O, so the stream assignment schemes are based on data units. AutoStream and LKStream are based on the characteristics of LPA chunks. PCStream uses program contexts, but there are also data lifetime differences in the above data units. And to obtain these characteristics, application code or kernel code need to be modified. This makes the deployment on product environments difficult. File is a natural data unit. It has 3 advantages. First, the access patterns of data within the same file are similar. Second, there are many file characteristics. Third, Linux provides some tools to obtain file characteristics, such as iNotify. For data files in various databases, we found 2 main types of files: append-only file and in-place update file. Append-only files appear more in key-value LSP-based stores, such as USB and Cassandra. These files are log-structured files. Data are usually not updated inside the file and are invalid only after the file is deleted. As data are updated, files are frequently created and deleted. In-place update files appear more on Circle database, such as MySQL and PostgreSQL. Data are updated inside the file and are invalid when they are covered. These files usually exist for a long time, and they are created or deleted when the tables are created or deleted. Let me first analyze the append-only file. The finger shows an example of create, write, delete of those GB files. We can get 3 observations. First, these files are frequently created and deleted. They finish writing very quickly, and a few files write at the same time. Second, the data lifetimes within the file are similar and can be reflected by the file lifetime. And last, the same type of files may have similar lifetimes, such as write-head logs, while different types of append-only files usually have different lifetimes. Next, in-place update file. The finger shows an example of table files writes in MySQL and PostgreSQL. We can see that the update frequencies of data in different files are quite different, and the update frequency in the same file is relatively similar. The update frequency is related to the data lifetimes, since data are invalid when they are overwritten. We propose the unit size modification, the ratio of the number of modifications to the file size, to reflect update frequency. The architecture of our file stream is shown in the finger. File monitor captures file characteristics and stores them in the file attribute table. Stream manager maps or remaps each file into a stream based on these characteristics. Stream manager has three modules. Mapper assigns stream IDs to files when they are opened. Remapper will assign the stream IDs to non-opened files. And divider allocates different stream IDs for the mapper and the remapper. Next, we will introduce these three modules in detail. First is about mapper. Some files complete writing very quickly, as in many open-only files, so it's necessary to assign a stream ID to a file when it's opened. That's what mapper does. Since the data lifetimes within the file are relatively similar, our first idea is to minimize the mixing of data between different files. We estimate the amount of data to be written in existing files. Smaller amount Fi means less data will be written to Fi, and thus less data will be mixed with the new file. Our second idea is to minimize the lifetime difference between files written to the same stream, since most of the newly opened files are open-only files, and their lifetime can represent the lifetime of their data. In order to estimate the lifetime difference between Fi and Fo, this equation calculates the average lifetime difference between the files of the same type with Fi and Fo. We consider files with the same parent path and extension as the same type of files. Smaller DIF Fi and Fo means the lifetimes of Fi and Fo are more similar. Then we want to combine the above two factors, so we multiply them, and we integrate the scores of the existing files of stream S as the final score of the stream S. Suppose the new file is mapped to the stream S. A smaller score indicates that less data of different lifetimes will be combined within the stream. Therefore, mapper selects the stream ID with the lowest score and assigns it to the new file. Next, remapper. Some files remain open for a long time, as in many in-place update files. They may face the changes of workload stress. Remapper is responsible for reassigning stream IDs to non-opened files regularly. As I mentioned before, the data lifetimes of these files are usually related to the update frequency of data, and we propose USM. We cluster files based on their USM by keys every t seconds. As the update frequency changes, the file will be remapped to a corresponding stream. Then we think that when the workload is stable, the clustering operation is not necessary. So before each clustering, we calculate the distances between files and the previous cluster centers. If files are still closest to the previous cluster centers, we think the workload is stable, and thus skip the clustering operation. This actually reduces the resource consumption and the fluctuation of the remapped stream IDs. Divider is responsible for dynamically allocating different stream IDs for mapper and remapper. That's to say, adjusting D. We consider who manages more files, or whose files more data are written to, who should occupy more streams. We calculate the proportion of the stream that mapper should occupy by the number of files managed by mapper and remapper, and the total number of their modifications. Then we adjust D and run D regularly. Next, we show our experimental results. We evaluated the file stream of real Samsung multi-stream SSD. It supports 8 streams. The experiments are performed on 6 workloads, as shown in the table. We compare file stream with a baseline without displacement and 3 existing displacement schemes. AutoStream and LKStream are automatic schemes. They assign the stream IDs to IO based on the exact characteristics of LBA. ManuStream is a manual scheme. Programs analyzes the application mechanism and fix stream assignment strategy into application code. In addition, the key parameter T is set to 1 minute by default, and is discussed later. This figure shows the rough values of the file streams on the 6 workloads. We can see that file stream significantly reduces rough compared with other schemes. File stream performs well on all 6 workloads. This figure shows that file stream improves throughput compared to other schemes on most workloads, and it performed very well on ZCD and Cassandra. Then, we verify the effectiveness of each module in file stream on 3 workloads. ZDB has many frequently created append-only files, so Mapper performed better on it. MySQL has many long-term in-place update files, so the Mapper performed better on it. The combination of these 3 modules makes file stream optimal. T is a key parameter in file stream, so we discuss it. In general, we can see that file stream is not highly sensitive to this parameter. This table shows the CPU usage of baseline and file stream. The increase in average CPU usage and peak usage is negligible, so file stream doesn't consume much resource. Finally, our achievements are summarized as follows. First, we propose a file-based automatic stream management scheme. It greatly reduces WAF and improves the performance of SSD. Second, we propose to estimate the mixing degree of data with different lifetimes to separate the data of newly opened files. Third, we design a new feature to reflect the access patterns of long-opened files, and we use machine learning to group files. In the future, we will apply our scheme to more devices such as zoned namespace SSD. It streams to hundreds of zones. We may also combine file information and LBA-related information. That's all. Thank you.